Hello everyone. I'm Faheem from the University of Adelaide, Australia. First of all, I apologize for not making it up to the conference. In this presentation, I will talk about adaptation for big data cybersecurity analytics. More specifically, I will first introduce the topic that what is big data cybersecurity analytics. Then I will go into the background that led us to the research problem being addressed in this paper. Then I will present the proposed solution. Then I will move towards the evaluation and what results we obtained. And finally, I will conclude the presentation. So we all know or are familiar with these systems like intrusion detection system, security information, and even management systems or malware detectors. Now, what happened with the passage of time is that the amount of data that is generated and that is to be analyzed by these systems, it has grown exponentially. The volume, the velocity, and the variety of these data. So this problem has given birth to a new class of systems that is what we call big data cybersecurity analytics systems and shortly BDCA systems. These systems basically use big data technologies like Hadoop, Spark to collect, store, and analyze this large volume of data for various security objectives, such as detecting cyber intrusions. We did a study on the quality attributes of big data cybersecurity analytics systems, and we found that accuracy and response time are the most important quality attributes of this class of systems. Now, what we mean by accuracy and response time is accuracy measures the ability of these systems to accurately detect cyber attacks and not become a shield in the face of legitimate access. And response time measure that how quickly these systems can be analyze and generate the alerts, which are then used to contain the attack. So the more quicker a system is, the better it is, and the easier it is to contain the attack. Earlier this year, we presented this work on architecture-driven adaptation for big data cybersecurity analytics systems in International Conference on Software Architecture. The main idea behind that work was that we have a component-based architecture for a BDCA system where we throw out the various functionalities into components, and we don't have each component operationalized at each time. Rather, we have our configurations, and at a particular time, a particular configuration is operationalized, and according to that, the system operates. Now, what we do is that we introduce this adaptation layer, as you can see on the top, and that adaptation layer measures the quality of service of the system. So, and the quality of service is calculated using the utility function shown at the bottom of the slide. Now, whenever there is a change in the data set that is being analyzed by the system, the adaptation layer measures the quality of service, and if the quality of service goes out of the pre-established quality of service threshold, now the adaptation layer, it has to bring it down. Now the way it brings it down is by selecting another configuration. So essentially what this adaptation layer does is that whenever the quality of service goes out of the threshold region, it executes and then finds a configuration that has a quality of service within that threshold region. The issue with that approach was its adaptation time. The adaptation time was high. It was around 751 seconds on average. Now, why it was high? The adaptation time was high because the configuration space is large and finding an optimal configuration is time consuming. Because in that approach, we had to calculate the quality of service for each configuration, and then after calculating for all of them, we can pick up the best configuration. Now that led us to the research problem that is addressed in this paper, and that is how to enable a BDCA system to quickly adapt to the changes in the security event data, which means that the adaptation time is high and now we have to reduce the adaptation time. So this is what we did in the previous paper. We call that approach adaptics, and the main idea was calculate the whenever there is a change in the data set, calculate the quality of service, and if it is below the threshold region, then calculate the quality of service for all the available configurations and select the configuration with the best quality of service. Now here in this paper, we followed a different approach. What we did was that instead of looking and monitoring the quality of service, why not look at the input data and do some descriptive statistics of the data. So the approach, the way it works is that whenever there is a significant drift in the data that is fed into the system, we calculate the descriptive statistics of that data. And by that, we mean that like number of instances in the data, number of features in the data, number of duplicate instances in data, and so on and so forth. And then we have formulated some fuzzy rules that help us to select the optimal configuration. So instead of searching the space of configurations, executing them, and calculating the quality of service, we directly use those fuzzy rules to select the optimal configuration. The basic principle is that select a different set of components based on fuzzy rules for each type of data set. These rules we have formulated it based on experiments and then also taking some guidance from the literature on big data cybersecurity analytic systems. As an example, there is a component, signature-based detection component. Now, for this component, we rely on two variables from the input data set, number of features and the test sample size. If the number of features and test sample size is on the lower side, then this component is operationalized. Why it is operationalized is because if we have large number of features, in that case, anomaly-based detector, which is operationalized by default, it works much better. And the test sample size, because if the test sample size is very large and then we have a two-phase processing of anomaly based detector and signature based detector, in that case we already have our giving up too much to the response time. So that is why whenever the number of features and the test sample size on the lower side, then it makes sense to operationalize this component. So the adaptation algorithm, the way it works is that the first we calculate the divergence between two data sets. If the divergence is statistically significant, in that case, adaptation is triggered. And when it is triggered, the first thing we do is we measured, we did some descriptive statistics of the data, and then we execute all these rules to decide that which of the components should be operationalized. We evaluated our approach, and our objectives that we had while evaluating was to first find out that how effective our approach QuickAdapt is in selecting the best architectural configuration, which means what is the adaptation accuracy. Then how long does it take for QuickAdapt to make the system adapt to the changes in data, which means adaptation time. Then how much optimization is achieved in accuracy and prediction time. And lastly, how it compares to our approach, our previous approach, adapting. The technologies that we used in our approach were in implementing our approach was we used Hadoop, we used HDFS, we used MapReduce programming model, and we used Mahout for implementing the machine learning models which are used in the anomaly based detector component. This is the configuration of the cluster. So we had one master and we had 16 worker nodes. These are the data sets which we used for the evaluation: KDD, DARPA, CIDD, SCI, CIDS 2017. These are the 5 algorithms which we used in our evaluation. We used Excel state for statistical analysis of the data, and we used UltraEdit software for manual navigation through the data sets. Adaptation scenarios in data drift. So we had two scenarios. One is the baseline where a system is analyzing a particular data set with the best configuration for that data set. Now what happens is that we change the data set from let's say from KDD to DARPA, and along with that, then our adaptation layer, it calculates the drift in the data using test statistics. And then when we have the divergence through this test, then we apply the p-value test to see that whether the divergence is statistically significant or not. And if it is significant, then in that case, adaptation is triggered. Now in our evaluation for all the data sets, whenever there is a shift from, let's say, from KDD to DARPA, the significance of the divergence is statistically significant, and so we have the adaptation triggered. So the first one is adaptation accuracy. We found that the adaptation accuracy is around 70%, which means that in 14 out of the 20 cases that we have investigated, our approach can select the configuration that is within the top 5 configurations. So by 20, I mean that we have 4 data sets and 5 algorithms. That makes 20 cases for us to evaluate. With respect to the data sets, DARPA and CIDDS has a better accuracy. Now on the left side, you can see all the configuration space where we have around 32 configurations, and on the right hand side, you can see the configurations that are selected by our approach with the help of those fuzzy rules that I have shown previously. Adaptation time, which is the most important aspect as for this work is concerned, it is around 7.1 seconds on average. Adaptation time is normally elapsed in calculating the descriptive statistics and then recomposing the system with a new set of components. And the largest the number of instances, the number of features in the data sets, the larger is the adaptation time for the data set. Optimization, now we look at that how much optimization we can achieve in with respect to accuracy and prediction time of the system. So our approach optimizes accuracy by 4.52% and prediction time by 17.6%. Optimization is higher for datasets with a large number of features, for example with KDD and with CICIDS 2017. Now we compare our approach QuickAdapt with the approach that we previously presented in ICSA that we called Adaptix. So the most important thing, as I mentioned about adaptation time, the adaptation time that our approach QuickAdapt improves by 105 times as compared to the previous approach. You can see it on the figure in the top right corner. As for the optimization in accuracy and prediction time is concerned, so Adaptix optimizes accuracy by 6.2%, and this one, QuickAdapt, it optimizes by 4.5%. Similarly, in prediction, with respect to prediction time, QuickAdapt optimizes by 17.6%, while Adaptix could optimize it by 26.1%. So the optimization is not as good as with Adaptix, but the gain in adaptation time is far higher than the loss in the optimization. So to conclude, the first thing is that our approach, QuickAdapt, it could improve the accuracy by 4.52% and the prediction time by 17.6% on average. But more importantly, the gain in adaptation time is around 105 times as compared to Adaptix. From this work, what we can conclude is that instead of uh, executing each configuration at runtime, calculating its quality of service, and then picking up the best optimal or the best configuration, the efficient approach is that we have prior knowledge in the form of fuzzy rules, and then we use those fuzzy rules and along with the descriptive statistics of the data to select the optimal configuration. And this approach is or more important in cases where we have the changes in the data set more frequent, because whenever there are more frequent changes, in that case we would have to adopt on higher frequency basis, and so we are more in need of a smaller adaptation time. In future, we aim to use machine learning for automatically generating, refining, and updating the fuzzy rules, because these rules are based on our own understanding and some preliminary experiments. But for these rules needs to be evolved as with the evolution of the system. And then in the current form, we did all experiments with batch analytics. So in future, we aim to do the same experiment for stream analytics. Thank you so much. Now, if you have any questions, I am available on Skype to answer. Thank you.